And we are on the air. Hello, ast111x. My name is Frank.
I'm Brent.
And I'm Becky.
And Jackie, who's the other TA, will hopefully be joining us soon. She's doing some other astronomy stuff right now. So for this hangout, I think we'll start off a little bit. I'll talk a little bit about the exam. I'll do a little mini module on time. And then I think Becky is going to talk a little bit about Planet 9. And then Brent will head up some of the topics that were suggested on the Google Hangout on our discussion thread. Okay, so why don't we go ahead and get started. Oh, and by the way, there's a group chat thing on, well, at least it's on my right side of the Google Hangout. So if you have any questions, you want to put something in the chat window as we go along, go ahead, and we'll try and pick it up as we go. Okay. So I'm going to cover a little bit about time. So I'm going to do a screen share. And I want to share this. Start screen share. People see my my slide?
Can see it.
Yep.
Well, I'll just scroll it. It's not being a nice slide thing. Okay, so as kind of usual, I'll start off with a quote. The passions of astronomy are no less profound because they are not noisy. And that is a quote from the main character, Pippin Herstal, in John Steinbeck's novel The Short Reign of Pippin IV. And Pippin was an amateur astronomer in France in 1950s. And it's the only political satire that John Steinbeck ever wrote. And sort of by a quirk of fate, he's a commoner, an amateur astronomer, as I said, and he becomes elected the King of France. And he finds the lack of privacy, the alienation of his family life, and all the uncomfortable trappings so bad that he often dresses as a commoner and rides around on a motor scooter, as shown there on the cover illustration, to sort of avoid the constrained life of a king. And so one of his quotes in there on the joys of not being king is that the passions of astronomy are no less profound because they are not noisy, meaning the political process is a little noisy. Eventually he gets his wish and he gets booted out as king, and so hence the short reign of Pippin IV. So we're going to talk a little bit about time through this, time through the ages, how humans have measured time, what some of the issues with measuring time are. No particular reason why I put this artistic drawing up. I just kind of like it. It's a clock. It's the Big Dipper. It's just kind of cool. Okay, 'tis the season. So originally when humans start off, you've got sort of an agricultural dependence, and that means knowing when to plant and when to expect the first frost and when to pick. And all that is driven by the sun, by the solar time, by the seasons, and there's no real issue. You just sort of follow the sun and you know what to do agriculturally. But as societies grow more and more complex, they start desiring to have fixed dates for things like festivals, like let's say the 4th of July in Tempe, which is shown there on the image, or your birthday, or when to pay taxes, or all kinds of things that we have fixed dates for. And as soon as humans do this, as soon as they introduce the desire to have fixed dates, this is what introduces the difficulty of keeping the seasonal calendar the same, the time that the sun says, versus the calendar year, which is the time that humans say. And so the entire saga is all about this synchronization of the two clocks, the calendar year clock, which we say the time is, and the seasonal clock, which is the time in a year. So what's a year? So just for reference as we go along, the seasonal year is defined as you go from vernal equinox, that's the spring equinox, to the spring equinox. Vernal to vernal is about 365 days, 5 hours, 48 minutes, 46 seconds, or 365.2422 days. And there's sort of our melting of the clocks there with the persistence of memory, Salvador Dali painting. So yearly calendars in the beginning were often based on going from summer solstice to summer solstice, or more often than not, when a particular star first rises with the sun, which is called a heliacal rising. And the Egyptians used the star Sirius, which is the brightest star in the sky. It rose in early July, and that's what this image shows. You've got Sirius there in the constellation Canis Major on the right. It's just going up above the horizon there. The sun is a little bit below the horizon, and if you look carefully at the information in the upper left of that figure, you can see this is from Alexandria, Egypt, in the year 2000 BC at some time. And so you've got this is what is meant by a star rising with the sun. So it comes up a little bit above the horizon right when the sun rises. So in Egypt, the heliacal rising of Sirius occurred in July when the Nile was in flood, and with an economy based on the Nile floods, the heliacal rising of Sirius was the most important day of the year, and hence the Egyptians made it their first day of the year, their January 1, if you like. But it takes place in July, and it moves around a little bit depending on exactly when Sirius would rise. So that's an example of a heliacal rising. Now, it's from that ancient Egyptians in Sirius. It is the brightest star in the constellation Canis Major. There's an artistic rendition of the dog constellation. And because it's in Canis Major, it's sometimes called the dog star. And it's from the Egyptians' use of the heliacal rising of Sirius in early July is where we get the phrase, the dog days of summer, which refers to deep July, and it's when Canis Major begins to rise. So that just turn of phrase has been around since the Egyptians with the dog days of summer, and it's still with us today as we go. So once you've got some idea of a year, whether you go solstice to solstice or heliacal rising to heliacal rising, that's a little bit too long for humans, so you want to start dividing it up, and so you want to start dividing up those time intervals within a year. So how do you do that? Well, the most obvious marker to use is the moon, and that is in fact the root word of month, moon, month. They go one to one. So if you're wondering where month came from, it means the moon. But there are two main obstacles with using the moon to subdivide the year. In the image there, the Aztecs had a calendar based on La Luna, and this is one of their lunar calendars going through there in stone. So the first difficulty with using the moon as a marker of time within a year is that the lunar month varies. It's not constant. It varies between about 29 and 30 days. And this variance is due to using the thing that you see, the synodic period, rather than the sidereal period. So the synodic period is the time between identical alignments, let's say of the sun, the earth, and some distant star. It's easily observable, but it's not so useful. The sidereal period is the time between an identical star, earth, and object alignment. We're going to show an image of this here. This is the true period. This is the real period. This is the period that you would stick inside of Kepler's third law, either in Kepler's simplified form or in Newton's fuller form. But it's also harder to observe and recognize the difference. So let's just walk through this a little bit on the difference between the two. So here we've got the sun, we've got the earth shown in blue going around its orbit, we've got the moon in purple going around its orbit, and then we have a background star in red there off to the right. And so we'll start this game when everybody's in the same line. So we have the sun, the earth, the moon, and the star, and in this particular alignment it's a full moon. The moon is on the other side of the sun. And we also have the moon aligned up with the star. So now you let time go forward. So the Earth goes around in its orbit, and that's the real reason why this happens. The Earth doesn't sit there, it goes around in its orbit. And then by the time that you get the Earth in blue, the moon in purple, and the star all lined up again, this is a period of 27.322 days. This is the real period. This is the sidereal period. But the moon is not full, right? Because the moon is not on is not opposite of the Earth. So the moon has to travel a little bit extra of a distance, shown there in the deep purple, to get back to the point where it's a full moon. And that extra period is variable. It can go anytime between 29 and 30 days, and that's the synodic period. That's the easily observable one. So that's one of the problems with using the moon as a delimiter of time in the year, is that the easily visible thing varies around a bit. The second obstacle is that a year cannot be divided by the average 29.5-day lunar month. The 12 lunar months is 11 days too short, and 13 lunar months is about 19 days too long. And so if you use such a calendar, a lunar calendar will slowly get out of step with the seasons, so that if you didn't do anything about it, the hottest time of the year would eventually occur during the winter months, which of course is not desirable. You want summer to be summer. And this is a real good example of the difficulty of keeping the clock with what the sun says with the clock that humans want to have, where you've got fixed dates for things and you want summer to be summer. And there's an example of the discrepancy if you try and impose an order on it. So many cultures got around this conflict by inserting an extra 13-month every couple of years, so that they could keep the seasonal and the calendar years, the human calendar years, would stay aligned. So summer would be summer, and we'd have our fixed dates for whatever we wanted to do: pay taxes, celebrate various birthdays, and so on. And it is from this marking, using the moon as a marker, that we also get all kinds of other phrases in English language. So it was kind of accepted practice in Babylon 4,000 years ago that for a month after a wedding, the bride's father would supply his son-in-law with all the mead he could drink. So mead is a beer. It's a honey beer. There's an example of one there that's still made in Oregon. It's a mead. And since the Babylonian calendar was lunar-based, this period was called the honey month. And this is the origin of where we get the term honeymoon from. Although I'm not sure it's common practice that the bride's father buys his son-in-law all the beer he can drink for a month anymore. That's kind of the origin of it, the honey month. The moon also gives us all kinds of other fun phrases that we won't get into now, but we get things like lunatic, for luna, a blue moon, a wet moon, a harvest moon, etc. And there are more of them, all from using the moon as a calendar marker. So the Egyptians, by the time they came along, they'd had enough of that. And they gave up on using the moon to mark time within a year and took a much more radical approach. So it is from the Egyptians that they divided the year into 12 months of 30 days each, for a total of 360 days. And 360 days is, of course, very close to 360 degrees in a circle. And that's where it comes from. That's why we have 12 months at 30 days, because it's 1 degree per day as it moves around. And at the end of every year, they added 5 days for an approximation of 365 days. And then extra days were sort of randomly added to keep the seasonal and the calendar year synchronized. And this technique is going to play out throughout time, even up to the present, of adding time to keep the seasonal and calendar years synchronized. So time goes on, Romans become the world power, and they had a surprisingly messy calendar. A year was only 10 months long, with March being the first month of the calendar year. So March 1 was like the January one we have today, and we'll see where January 1 comes from shortly. But 10 months, and March was in the first. And extra days were inserted at random, again, to keep the seasonal and calendar years together. There's an example of a Roman calendar there in the image. And the Roman calendar is still with us, because the very names of the months, September, October, November, December, these are from being, if you speak any sort of a Romance language, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 7, 8, 9, 10 in Spanish there. Those are the 7th, 8th, 9th, and 10th months of the Roman calendar. Although for us in the modern era, of course, that's the 9th, 10th, 11th, and 12th months of the year. But the origin of those names goes all the way back to the Romans and their 10-month calendar. So 1 year before his death, Julius Caesar had had enough of this nonsense, and he decided to implement a new calendar. And so the Julian calendar has 12 almost equal months. March is still the first, the Ides of March. He still keeps that, for totaling 365 days. And so now he's going to organize, so he hasn't done much yet, really. But now he does implement a real change. And he goes that every 4th year, we're going to have a leap year, or 1 extra day is going to be added at the end of the year. And so the whole notion of a leap year, an extra day in February before March, because March was the 1st, so we're going to tack on the extra day at the end of the Roman calendar, that would add it on. And this would give an average of 365.25 days, which is pretty good. Okay. And so Julius liked his new, more accurate system so much that he decided to name a month after himself. And this is where we get the name July, for Julius Caesar. And I think that's kind of funny. But that's not the end of the story. Politics love money, and money loves politics. And so at the time of Julius, one of his most powerful backers was a family known as the Juno family. They were the ones with the money. And in order to honor his money benefactors, he gave them a month too. And so from the family name Juno comes the month of June. And that's where we get that one from. Of course, now the pattern's set. And so every Roman emperor after Julius has to take a month and name him for himself, because he must be just as important as Julius was. Fortunately, the only one that stuck was Julius Caesar's grandson, Augustus Caesar, and that is where we get the name of the month August for Augustus Caesar. So lots of our month names are due to the Romans. So Julian's calendar is pretty good. He introduces the leap year, but it's still not quite right. The Julian calendar is about 11 minutes too long, or it'll be off by 1 day in about 130 years, or about a week after 1,000 years. Goodness, 1,000 years, that's so long, who can think about it? It's good enough. Well, guess what? 1,000 years went by. And so by 1582, the seasonal and calendar years were about 10 years out of sync. And so Pope Gregory introduced what is known as the Gregorian calendar. And take a look at this calendar here. 1582, October. What do you notice? You notice that the days go 1, 2, 3, 4, 15. So the first thing he did to get realignment of the season and calendar year was just to chop 10 days out of the year. And this caused social panic, near riots, because I miss a payday, my birthday's gone, all kinds of things. You just chop 10 days out of the year. Ah, panic in Detroit, or panic in Rome, as it may be. So he chops 10 days out of the year. And because it's Roman Catholicism, we can't have that paganism beginning of March for the first of the year. And so it's from Pope Gregory that he changes when the beginning of the year is. So this is where we get January 1 as the start of the year. But he does keep Julius's extra day in February. So every 4 years, an extra day is added to February. So far he hasn't done anything. All he's done is sort of realign the calendars again, and he shifted where you call the origin. So, okay, it's January 1 instead of March 1. Okay, no big deal. But now, as an attempt to make it more accurate, he adds a new rule, that century years divisible by 400 are leap years. So 1700, 1800, 1900, those are not divisible evenly by 400, and so they are not leap years. But 1600, 2000, 2400 are leap years. And when you go through that, this new Pope Gregory system, or the Gregorian system as it's known, is just 38 seconds short in a year, or 1 day every 2200 years. So what are we going to do? Are we going to go through the same game and wait 2,200 years before we have to chop out some days and add another rule? No, we don't do that anymore. That's over. So what we do these days is we add 1 second to the calendar clock at midnight on one of two dates, June 30th, excuse me, or December 31st, whenever the difference between the seasonal year and the calendar year reaches 1 second. So we're not going to wait for it to build up to 11 days or some crazy amount. We're just going to adjust it kind of on the fly as we go. So the calendar clock, these are human clocks, is maintained by an international bureau in France, and they use a worldwide network of atomic clocks to set the calendar clock. The seasonal clock, what the sun says the time is based on observations of Earth's rotation. And it's done by the International Earth Rotation Service, and there it is on the right there, that image. This is actually part of the function of the U.S. Naval Observatory, is to know what time it is by the sun. You already know why there are 7 days of the week, because there's only 7 things that moved on the celestial sphere, and they all got their own names. Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, from the North Celtic gods. So that you already know. We covered that in the lecture, but one thing you may not know is, where did time zones come from? Who invented that? Where did that invention come from, and why would anybody do that? So this is sort of the modern time zone carving up. It's not a straight line almost anywhere because there's geopolitical realities. And people can call it whatever they want. But where this comes from was from transportation industry. Before time zones came in, every region set their clock according to the local conditions. You know, noon was when, you know, it was the sun was directly overhead, and so noon, for example, in Tempe would be different than noon in Yuma, Arizona. They're just separated by a little distance, but their local conditions would be different. And this caused major confusion as to when trains were supposed to arrive or depart. Whose time zone, where are you talking about? And so it was the railroad industry in the United States that set up the 4 time zones. That everywhere within this band, we're going to call it the same time. And then that was such a great idea that in 1918, the U.S. Congress made the rail zones official under federal law, and then shortly thereafter, in sort of the mid-1920s, is when the equivalent of the United Nations at the time standardized it across the globe. And that's kind of where time zones come from. And that's what I have to say a little bit about time and where it comes from in the years and the months. Okay? So I'm done with that, and let's, and I guess I'm done screen sharing.
I was going to talk about Planet 9 next, I think.
Sure.
Sorry, my screen share is not working. All right. The question on the forum was about Planet 9. For some of you, I'm sure, haven't heard of it. It's basically, there's a lot of evidence showing up, which I will talk to you about, that indicates that there is going to be another planet in our solar system. And it would be an actual planet, because it's going to be some like 10 times Earth mass. So it's going to be even bigger than Earth. But we haven't found it, we haven't seen it yet. So, okay, just screen share. There we go. All right, so I think one of the biggest problems that we have sometimes is understanding the distance and sizes of these things. So this is actually a comic from XKCD, and the axes are, this is how far it is from you, and then this is how big the actual planet is, or object, since I guess they talk about everything down here. So the interesting things I figured were stuff that actually is related to space. So Earth and the Moon and these planets over here are in like the planet category, and they're all roughly, you know, 10 to 100,000 kilometers away, but they're within a rather small area. So the difficulty with Planet 9 is you can see it is much, much further away. These planets here are the ones we can see just with the naked eye. These two are Neptune and Uranus, and we only can see those through telescopes, and then Planet 9 is way out here. So it's one of the reasons we haven't identified it yet.
I just want to say that I haven't seen this XKCD plot before, and it is great. It's a fantastic plot.
Yeah,
I really like
it made me laugh a little bit. It's like planets ruled out because I would be inside them because they're too big and too close. So I'll post a link.
It's also really useful too. Super great.
It is. And then up here, I just want to point out, it says planets ruled out because we would see them during the day. That's because these would become stars. They're so big. So they're so big and so close. So there we go. All right. So there we go. This is sort of like the basic, very basic outlines of Planet 9. So just by size, if you were to say Earth was 1 Earth mass, then Planet 9 is about 10 times that amount, so 10 Earth masses. And so it would be somewhere between Earth and Neptune in size. And the length of a year down here is what they're saying, like every planet is going to have a different amount of time to go around its orbit. And Planet 9 would take tens of thousands of years to go all the way around its orbit. It's one of the reasons we haven't seen it yet. So the reason we believe that there is probably a 9th planet is because there's 6 dwarf planets that are really, really far out. They're well outside of the orbit of Neptune and Pluto. And you can kind of see right here how they sort of align with each other. The argument is actually more than just how you see how they have their perihelion right here. It has to do not only with that, but also their the angle of their orbit to the like the sun and the ecliptic, and then also how close they are. And when you combine those two parameters, those two things, why are you not moving? You get the this angle that matches up. Oh well, okay. All right, sorry, I should have pulled this part up. So if this was our solar system, just ignore the random letters. But if this was our solar system, then the objects that we're talking about would be at an angle. This would be the like an orbit at an angle to the solar system, and so it depends on where it crosses our into the solar system and how close it is when it does. So that's kind of a complicated question, so just the basics. So you have these 6 objects that pass through the solar system's ecliptic and come close to the sun at really, really similar numbers. And so this first part with these 6 planets, that's what made people believe there could be something else. But there were some predictions that if there were a bunch of planets that had the same, they called it argument of Parasis. If they have that same alignment, then there would also have to be the same type of objects, only with orbits that are at 90 degrees. And so one of the big reasons we have for thinking about that is that when they made these predictions, they said that there had to be these orbits at 90 degrees, and when we looked, there they were, exactly where they were supposed to be. So there's a lot of evidence, but we still haven't found it yet. Part of it is because it's so dim, and part of it is because we would only know it's a planet if it moves in the sky. The further you are from the sun, the slower your orbit is. So we may have seen it and not realized what it was, although it's not considered that likely. or maybe it's just we haven't looked in the right place. The other problem, though, is figuring out... Okay, I guess I don't have that image anymore. Nope. The other problem is figuring out where exactly the planet is. So it may look like this is like a really specific place for the planet, but we don't know, we're not sure exactly where in the orbit the planet is. And this is a lot of orbits that match this somewhat closely could still be really far apart just when you're looking at the telescope. I guess that makes sense. So there are scientists that are doing models. Basically, they're putting a bunch of these, the orbits that they can see into model as well as some of the formation, how the planet would have formed into a model to see if they can map the orbits close enough to get even closer position on where Planet 9 is. And they are calculating what kind of stuff the planet might be made of and how bright it would be if it had these different, you know, if it was made of something more like Neptune and Uranus, or if it's more compact or cooler than that. So the telescope they plan to use is called Subaru. It's in the northern hemisphere, so we can actually see it from the northern hemisphere, hopefully. And it is a 8-meter telescope. So the diameter of the telescope is 8 meters. So we do know some things, and there's a lot of things we're guessing right now. And where's the hangout? All right, I give up. There you guys are. So yeah, I don't know if there was any questions about that. I don't see anything, so I will pass it along to Brent.
Okay. I have one question on that. Maybe you've seen it while you're doing your research. Is there any other possibilities that it could be multiple planets and not one 10 Earth mass planet?
They didn't really talk about it that much. My assumption was that if there were multiple objects, then you wouldn't end up with that really, really nice alignment because the two different ones would argue with each other. So it has to be one large object so that everything can align that way.
Yeah, I think it's a stability argument. It's kind of why it's hard to put a planet around 2 or 3 stars, right? So if you have several of these things, you'd scatter all those things all over the place.
I see.
I mean, you could have a double planet scenario where they're orbiting a common barycenter and they're very close together, so that from every other object in the solar system's point of view, they're approximating a single planet because they're so close together. But aside from them being close together, or it being like it could have moons, but they're going to act as a single planet from our point of view.
Okay.
You probably can guarantee that it has something resembling moons around it just because it's moving through the field of stuff. But.
And this is the only planet that's been kind of theorized to be there. Do they think there could be like even more potential planets?
I don't think they have any evidence one way or the other if there's more. If there are planets further out, they are not having any effect on the rest of the objects we can see. So it's likely we still have more of those things that are like Pluto-size, the dwarf planets. There's probably way more of those, but I don't think they think there's anything this size. This is about the last really big planet.
And for a long time, there was this discussion about Nemesis, this hypothesized brown dwarf that was living sort of halfway between the Sun and Alpha Centauri, and it would sort of dive bomb the solar system every thousands of years. But we're talking about much farther out, maybe even than this object, and this object is quite far out. So, and I don't think I've ever seen a really convincing argument of that. And then the next level out, there's I think Mamachek et al. Had a paper recently in the last year about a red dwarf that actually is leaving our solar system. It's not part of our solar system, but it sort of dive bombed our solar system and is actually on its way out, and they could sort of tell from its proper motion that it had just finished doing a close encounter. So I don't know if we're actually going to expect to see some kind of like incoming Oort objects from that, because an object like that can disturb the Oort cloud, but I have no idea what the expectation is there.
That's pretty interesting.
I think they're focusing on like the more simplified ideas right now. Just stick with the one planet and hopefully find that. It's also the one thing that they know they can find. You know, if there are further objects out there, they're focusing on the one that they are likely to find. So.
Okay. So there was a post by Morgan Kemp asking about astronomical units, and I'm assuming that he was talking about AU, as in the average distance between the Earth and the Sun. So I guess I did a little research on an AU, what constitutes an AU, how it's defined. So basically, an AU is defined as approximately the average distance between the center of the Earth and the center of the Sun. But it's not exactly that distance. It was actually defined to be fixed at, let's see, 149,597,870,700 meters exactly, which is about 150 kilometers. And this was defined similar to how the speed of light was defined, how it just by convention it's defined at this fixed value. And meters were actually defined by the speed of light after fixing the speed of light at its value. And so the reason why this had to be set to a fixed value is because the average distance between the Earth and the Sun actually varies every year. And this is because of gravitational effects from the Moon and, to a lesser extent, other massive bodies in the solar system. And it can vary. Well, see, for example, the last perihelion, which is the closest part of the orbit of the Earth and the Sun, or in general, it was at about 0.98 AU, and this happened on January 2nd. And the perihelion actually occurs about 2 weeks after the winter solstice, but it changes, of course. And the aphelion, which is the furthest part in the orbit, it will occur on July 4th this year, and will be about 1.017 AU away from the Sun. And this occurs about 2 weeks after the summer solstice. And so perihelion, closest, meaning it comes from the Greek word peri, meaning close, and helios, meaning sun, and aphelion is apo for far, and helion for sun. And the next year, next year the aphelion will be about 0.003% larger than this year, and the perihelion will be about 0.00075 AU smaller than this year. And this is basically due to changes in the eccentricity of Earth's orbit from the gravitational effects I mentioned. And the time that it changes from between years could actually vary by a day in 48 years, or sorry, 58 years. So this is basically because the position of the aphelion and perihelion actually shifts every year slightly. And it can shift by about 2100 kilometers, as well as the aphelion, which is about 1.7 times the diameter of the Earth at the equator. And another interesting thing is that the perihelion and aphelion, the time between each, for example, the time between each perihelion can actually be longer or shorter than the year. And this is, of course, because the actual position of the perihelion in the orbit, it shifts in space. And one more thing about the AU is that AU is also used to define another unit called the parsec. And the parsec is the distance. If you imagine you're looking at a star or any body that's far away, it's the distance that from you to the star when it moves across the sky, it subtends 1 second of arc, which is 1/3600 of a degree. And so when the star shifts along that angular distance, the actual distance it moves in actual physical units is 1 AU. So it's actually defined to be that that distance in motion. And parsec is actually quite a big unit. It's 3.26 light years, or 31 trillion kilometers, or about 20,000 AU. Or wait, sorry, it's 20,000, I think. Or sorry, it's 2 times 10 to the 5 AU, pretty much. And so, yeah, essentially, an AU had to be fixed because of the perturbations in Earth's orbit. So, I think that answers his question. And he also asked about what constitutes the arrival to a planet. I would say if you're entering a planet, you probably want to probably touch down on its surface. And for a star, I'd say entering the solar system is probably as close as you want to get to the star. So maybe within its general what is it? It's like as far out as the solar winds affect anything.
The heliopause?
Heliopause, yeah, exactly. So I would say that's probably when you enter the solar system officially. And then there's another question about studying astronomy and what's a good pathway one would take in order to pursue astronomy professionally. So basically, just take a lot of physics and math. That's your best bet for becoming well versed in astronomy. I mean, there are, of course, well, at least astrophysics, because that's pretty much what we do study, is astrophysics. Astronomy is kind of like a more of a hobby, really, as in observing, like, and knowing, like, constellations and stuff. That's more of like a hobby thing, I think. But for professional astronomy, you need to know lots of physics and math, and probably programming will help a lot. And yeah, writing, getting a lot of practice in writing will help too, because that's what we do, is writing papers on everything we research and hopefully publish. So would anybody else want to chime in on that question at all?
I mean, what you said is what I did when I was in high school, and people asked me what I wanted to be when I grew up. And somewhere in there, I started saying an astronomer. And before I was willing to really commit to it, even at the level of majoring in it as an undergraduate, I sort of already knew I needed to be good at physics. And so I actually, as soon as my junior year in high school, so I was like 15 or 16 years old, I actually took advanced placement physics, which not every school even offers. But if you can take a physics course as soon as you can, if you can take a math course as soon as you can, and one of the problems that we're having with astronomy and getting people into astronomy is that, especially in the American public school system, a lot of people don't even have a good option for pre-calculus. And so if you're in one of those school systems where you don't have good math, outside of America, obviously it's going to be a completely different situation, but you need to find a way to cover the gap, the math gap, and get through calculus. And you need to be able to do calculus-based physics. And at that point, if you have convinced yourself that you can handle the math and you're good with the physics, at that point, go whole hog and go for astrophysics as a collegiate degree. But you do have to have the some kind of Bachelor of Science to be a professional astronomer. Really, these days, you have to have the PhD, which is going to require that you need to have some kind of bachelor's, which will allow you to do the PhD. And that could be any kind of science, math. It doesn't have to necessarily be astronomy or physics, but you're going to want something that made you take some physics and made you take the math through the calculus sequence, and preferably some linear algebra and statistics as well. And it's a nightmare.
Yeah.
Nobody thinks that's fun. Oh, that's not true. There's like 3 people who think that's fun. We call them theorists. Hi, Frank. And,
yeah, something I was going to throw in there was just like, we pretty much, like she said, pretty much all of us hated those classes. Please do not think that that's what it's like.
If you loved it, be a theorist. Otherwise, the two paths are observational astronomy and instrumentational astronomy. And instrumentationists like to build things, and observational astronomers actually use telescopes to look at things. And that would be, I think, Brent and I are the observationalists here. But you can be an observational astronomer without being a professional astronomer and make really meaningful contributions to science. There are lots of people who do amateur astronomy and actually like find supernova, find comets. There's
a lot of transiting exoplanets right now. Astronomers have been doing really good with finding extrasolar planets.
And if you do like building telescopes and hanging out at night, but yeah, you're gonna have to buy some equipment, and you're gonna have to get yourself, at least at the bare minimum, a CCD camera that can take pictures with a good mirror on a good telescope. And people go whole hog and get themselves little robotic observatories that they set up outside their houses. But yeah, it's a pretty consuming hobby for amateur astronomers. We're not the best people to ask about amateur astronomy because that's the path not taken for us, because we went right to the math. So
until I got to grad school, I didn't know very much about how to operate a telescope. I grew up in Michigan. It's cloudy, always. So I didn't actually know how to use a telescope very well.
Yeah, I did my undergraduate degree at Case Western, and Case Western's in the middle of Cleveland, Ohio. And so we would do our astronomy labs, and we'd wander out, and we'd be like, so there are 5 stars tonight. That one's Arcturus. That one might be Betelgeuse. We're not sure. And that one's probably Jupiter. And that's it for tonight. It was really... There's so much light pollution in cities these days that nobody sees stars.
That's probably a good lead-in to your constellations.
So I will unmute the microphone. Okay. All right. So I'm going to talk about the constellations. We don't talk about the constellations very much in this course. So in this course, we talk about the solar system. We talk about the physics of light and gravity, which you will need to be able to talk about the solar system in any depth. And don't worry, there will be no calculus. It's really a very broad brushstrokes kind of physics and light. And we talk about the history of astronomy, which we've already done in the last week. But we do not talk about the constellations. And I'm actually sitting here right now at Arizona State University. I'm actually in a computer lab. I was actually, right before I did this hangout, I was teaching, covering for another teaching assistant at Arizona State University. And so if you saw this person coming in and I was like grading his stuff, during the beginning when Frank was giving his time lecture, if you like look in the little window, if you go back to early, I actually was getting my last student out so that I could attend this hangout. So normally at Arizona State University, we have the Astronomy 111 class, which is the lecture class, which covers all the material we have here. And we have a laboratory class, and the laboratory class covers a lot of the sort of stuff that we're doing in the online laboratories. But we also have a night sky component, which is missing from the edX class. We do have a component where we actually go out on the roof with little telescopes, and we look at the night sky, and we teach people a little bit about observing with the naked eye or with a telescope. And we obviously can't do that in an online environment. Nevertheless, there are a lot of people who come to a class like Astronomy 111x hoping to get a little bit of that. And so I'm going to try to give you just really quickly a little bit of the constellations in the northern hemisphere, the constellations in the southern hemisphere, but more importantly than that, I'm going to try to give you some resources so that you can learn about these things on your own. Because a lot of learning to star hop across the night sky in different seasons, this is a skill which you need to practice and which is self-taught. And the first thing you're going to need is to get out of whatever city you're in. If you already live in the mountains, that's great. Most humans these days live in cities, and cities create something called light pollution. And so when you walk outside at night, you can see 5 stars if you're in Cleveland, Ohio. If you're in Beijing, it's going to be like, oh, what are stars? You might see Venus. But if you're in a smaller city, you can start to see Orion. And so one of the first constellations that any of us learn when we start to look at the night sky is Orion. And Orion, so I'm going to start doing a screen share here. Orion is a winter constellation. So let's see if I can start to do my little screen share thing. Mute microphone, turn camera off. Screen share. Desktop. Start screen share. So one of the very first things that we ever see when we go out and start looking at constellations is Orion. And so does everyone, am I screen sharing now successfully?
Yes.
Okay, and you see Orion. So I don't actually understand why these lines blink in and blink out. It's kind of odd. But so the first thing, one of the first constellations we ever learn is Orion. And Orion's a winter constellation, and now we're moving into northern spring. So Orion is visible in northern winter or southern summer. And an odd thing about Orion is if you're in the southern hemisphere, then you're used to looking at Orion standing on his head. Fun fact, northern hemisphere people who have never seen this, when you go to the southern hemisphere, if you go to Australia or you go to South America or South Africa, Orion looks like he's standing on his head. And if you catch the moon at moonrise or moonset, the moon also looks upside down. It's very, very weird. So this is a northern hemisphere view of Orion, because Orion is standing up. And so the classic view of Orion is these 3 belt stars, 1, 2, 3 in a row. And the celestial equator actually passes through Orion's belt. So it's a very handy anchor point. And then he's got his 2 shoulders, and this upper one here is Betelgeuse. And if you are not colorblind, if you have good color vision, and you're reasonably dark adapted, Betelgeuse here will look red, because Betelgeuse is what's known as a red supergiant star. It's actually within probably its last, I don't know, 10,000 years of life. Frank can opine on that. And so I and some of my friends like to walk outside and look up at Orion and then like cheer Betelgeuse on. Any minute now, Betelgeuse is going to go supernova and explode. And I want it to happen during my lifetime because that would be awesome. And then we won't have Betelgeuse anymore, but it would be spectacular. And then down here we have his 2 feet. These are his 2 shoulders, Betelgeuse and Bellatrix. And then his 2 feet. And one of them is called Safe, and the other one is Rigel. And Rigel's quite a bright blue star. And then, you know, if you're in a dark site, a truly dark site, like you go out in the country, in Arizona, we like to go to the Grand Canyon, then you can start to trace out these other fainter stars with, like, he's holding a shield, he's holding a club, or sometimes a shield is actually more of a bow and arrow because he's a hunter. And he's got a little, attached to his belt, he's got a sword hilt. And this is actually quite an interesting region of the sky. This is where the Orion Nebula is. It's one of the biggest star-forming accumulations that's close to Earth. And that's where stars are actually being born. So the winter sky, or the southern summer sky, is actually a really excellent sky. And we're moving into spring. And springtime is less fun for looking at the sky. But if you go out early in the evening at 7 p.m., 8 p.m., you can still catch Orion before he sets. You can catch Taurus here. These are the Pleiades, this little cluster of stars. And this star right here is called Aldebaran, and this is the eye of the bull. And it's also a reddish star, like Betelgeuse. And so that's in the west. It's setting during the spring. And then later in the night, you'll start to see other constellations come up. So we're looking south. Here's looking south. So as all of this shifts over, you'll start to see a lot of not so much. So the last bright star that will set will be Sirius here. Sirius is called the dog star because it's in Canis Major. That's the constellation. And I don't see Canis Minor today. Okay, so Orion has 2 dog stars following him, Canis Major and Canis Minor. And I guess this is Canis Minor up here. So this is Procyon, but Sirius is the big bright one. And so if you look in the western sky, you'll see the 3 belt stars, and they'll kind of point towards the dog star Sirius, which is the brightest star in the northern or southern sky. So, and then this other bright one up here is probably Procyon. Here's a full sky view. So this is a little later in the night. At this point, 9 p.m.-ish, Orion has set. And one of the things I want you to notice when I show you these star maps is that they're backwards. I don't know if this is bothering anybody else, but so north is at the top of the screen, south is at the bottom of the screen, and then east and west are backwards.
It's not backwards if you hold it over your head while you're looking up.
It's not backwards if you hold it over your head. So if you take the screen and you literally take this screen and you hold it over your head and you aim north towards north and south towards south, while you've got this held over your head, boom, east and west will align with east and west on the Earth. But the whole reason that star maps are always backwards is because they're meant to be held overhead. So that's star map skill number 1. All star maps are backwards, east and west are backwards, and it's because it's meant to be held over your head. If you hold it over your head, it makes sense. So it's totally okay to do that when you're looking at the sky at night. To just take whatever map you're using and just hold it over your head. And everything will become clear. So here's Procyon over here in the west. So this is the dog star, the second dog star, not as bright as Sirius, and it's following Orion into the setting sun. And then there's the twin stars Castor and Pollux. You'll still see it, where there's this wonderful arc between Capella, Castor, Pollux, Procyon, and then it goes to Sirius, and then over to Orion, and it makes this wonderful little arc through the sky. But that's the old news. That's the winter sky. We're moving into the spring sky, and so in the spring sky, there's a lot less going on, but we still have some stuff. We have Regulus, Spica, Arcturus, And then over here, these constellations that are rising in the east, these will be the summer sky. And I'm not going to cover them in too much detail. We have Lyra with Vega, Deneb, and then the Altair is down here. So this is the summer triangle that's starting to come up in the east in this. But they're going to be more in June. Right now we have a wonderful view of the Big Dipper. And the Big Dipper is something that I actually don't get to teach all that much in my astronomy labs because it's down during the winter, but it's starting to come up. And so here's the Big Dipper, and this is how you find the North Star. So especially if you live in a bright place like Tempe, Arizona, it's hard to find the North Star because it's not that great. We have a second magnitude star, and the magnitude system is backwards. 0 is brighter than 2. -2. Venus is -4. But a 7th magnitude star, which 7 is bigger than 2, why would that not be good? The larger the magnitude number, the dimmer the star. Polaris is only a 2nd magnitude star, and it can be kind of hard to see from inside of a city. But if you manage to find the Big Dipper, it's actually quite a big constellation. If you manage to find the Big Dipper, then you take the bowl of the Dipper, and these are called the pointer stars, and you take the pointer stars and you draw a line through them, and they will point to Polaris. And that's how you find Polaris. The Little Dipper is even harder to see than the Big Dipper. So usually I just see Polaris and these 2 stars over here, and then I kind of have to imagine this part. And until I go to a dark side, I can't see it. But the Big Dipper is really quite obvious to me right now, even standing in Phoenix, Arizona. And then you can take the same 2 pointer stars and go backwards. Backwards through the bowl of the Dipper, through the pointer stars, will take you to Regulus. And Regulus is the heart of the lions. This is Leo the lion. And he's fun to trace out because he's a reasonable constellation to look for. And he almost looks like a lion. Not really, but kind of. And so Regulus is the heart. So we go back to the Big Dipper. The Big Dipper is really anchoring our spring sky. And we use the handle. And so with the handle, instead of the pointer stars, we use the handle, we can arc to Arcturus. And Arcturus is the brightest show in town in the spring sky. So it's quite obvious, it's overhead. So arc to Arcturus, and then spike to Spica. And Spica is in the constellation Virgo. It's in the constellation Virgo. And so that's the northern sky. What about the southern sky? So the southern sky doesn't look that different. I just flick between them. Oh, it's not that bad, right? Not that. Here's the southern sky. One of the first questions I always get with the southern sky is, how do I find the south celestial pole? And the southern sky, so if you're in the southern hemisphere, you'd like to have a south star, the way the northern hemisphere has a north star. And the bad news is they don't. There's no convenient even 2nd magnitude star. There's nothing. Nothing. So the way you find the south celestial pole is you use the Southern Cross and then these 2 bright stars in the constellation Centaurus. And you'll note that this is southern autumn corresponds to northern spring. So I'm going to say southern autumn. It's kind of confusing. But if you're in the southern hemisphere right now, it's fall. Just like in the northern hemisphere, it's spring, because everybody's backwards. Southern autumn actually has got quite a good sky, as opposed to the northern hemisphere, where it's a bit empty. So they have Sirius over here, they have Canopus, which is the 2nd brightest star in the sky, and then over in the constellation Centaurus, and Alpha Centauri is over here somewhere. So these constellations here, these stars here, these are the southern pointer stars, and then we have the Southern Cross. And there's 2 ways to look for the southern celestial pole. One is to take the Southern Cross, and this bit here, this long bit, and just make it 4 times longer. Extend 4 times past the Southern Cross. 1, 2, 3, 4. And so the southern celestial pole is here. Another way is to draw a line through that, and then draw a line through the pointer stars. So rather than aligning the pointer stars, you just sort of take a line perpendicular to them. Sort of do a line perpendicular to them through them, and then another one like this. I think there's a drawing, actually. Here we go. Okay, so we take these 2 stars in Centaurus, these 2 bright stars that are next to each other, and we draw a line, and then one through the Southern Cross, and where they meet is quite close. It's not exactly right, but it's very close to where the South Celestial Pole is. And then if you keep going, you'll encounter the two Magellanic Clouds. And the Magellanic Clouds are kind of out of season for them. They're kind of low in the sky. They're better in southern spring. But there are two fuzzy blobs which correspond to two galaxies that are actually outside of the Milky Way galaxy. So you're actually looking outside of the Milky Way galaxy when you see these things. They really look like clouds. You really think you're looking at a cloudy sky at night. I've been in Australia and I've seen them, and I really thought, I didn't think they were extraterrestrial at all. I really thought they were clouds, but they never moved. They just stayed there. They're fuzzy blobs, but they are cool objects astronomically because they are satellite galaxies of the Milky Way. I'm going to end the screen share. Oh, I wanted to talk about planets really quick. Planets. Some of you may have heard that in the last month ago, there was this rare opportunity in January and February to see all 5 planets: Jupiter, Mars, Saturn, Venus, Mercury. You had to wake up at 3 in the morning to see them all 3 of them, and I managed to wake up at 3 in the morning, but I never could pick Mercury out. Mercury is always very hard to see because it's so close to the sun. So the sun starts coming up just when Mercury becomes visible above the horizon, and then you lose it anyways. So I never saw all 5 of them, but I did see 4: Jupiter, Mars, Saturn, Venus. Now Venus and Mercury are both moving behind the sun, and we're not going to see them again. Mercury will reappear in June. Venus will reappear in July and August. It'll start to get really good. It'll reappear as a evening star. So they're both going to go behind the sun. Right now they're morning stars. They're going to reappear as evening stars in the late summer. But we're still going to have Jupiter, Mars, and Saturn for a while. So when you go out at night and you see a bright star rising in the east later in the night, that's usually going to be Jupiter. You can tell it's a planet because it doesn't twinkle. Stars twinkle, planets don't. And I can explain that later in the discussion board. I don't have time now. Stars twinkle, planets don't. So if you see a steady, untwinkling thing rising later in the night, it's especially if it's like rising right where the sun would, and along the ecliptic plane, that's probably Jupiter. Earlier in the morning, in the wee hours, you'll start to see Saturn and Mars come up. Saturn and Mars are in... I think they're both in Scorpio right now. So they're going to be really nice in the summer, and there's going to be some really cool things going on in the summer months with those. And I'm going to end the screen share, and I'm going to show you my resources really quick. How do I end the screen share? How do I end a screen share, guys? Ah, okay. Goodness. So my resources that I suggest you get if you want to learn about the night skies. First of all, get yourself a star wheel. And this is something that we actually have our students get for the labs. We have them get a star wheel, and you want to make sure it's appropriate for your hemisphere. This is the night sky, but it's actually for 30 to 40 degrees north latitude. This is inappropriate for the southern hemisphere, and it's actually not that great if you're at equatorial latitudes in the north. So this is good for continental North America. Europe, you're going to want a 40 to 50. Mexico, you're going to want a 20 or a 10 degree. So it's not going to give you quite the right stars. Star wheels, this center, everything rotates around Polaris. So there'll always be a pin in the middle, and that's where Polaris is. And then what you basically just do is, it says north is right here, so you find north, south is over here. Okay, we'll turn it upside down. And again, like any star map, you're going to hold it overhead. You're going to want to look at it overhead. And you want a red flashlight, because red flashlights will preserve your night vision. So get a flashlight that's either a red LED, or you can get some red cellophane paper and put it over a white flashlight. And that way you can look at your map and look at the sky, and you haven't blinded yourself. And you want to match the month, the date of the month. So the wheel has dates on it. And it also, on the inside wheel, has times on it. So you want to match the dates. So I'll find April and March. Let's go with March 25th. March 25th. And I want to see what the sky looks like at, say, 9 p.m., which is about as far away as I could possibly be. March 25th at 9 p.m. And this actually gives me some idea of what the sky will look like March 25th at 9 p.m. And I don't know if anybody can see any of that. Brent, can you mute?
Oh, sure.
Thanks. I don't know if anybody can see any of that. Can you guys still hear me?
Yeah.
Okay. So, it's weird. Okay. So this is what the sky should look like right now. We also give students this Audubon guide. So this is the Audubon guide. Why can't I get the big screen? Did I have the big screen during my screen share? I did, didn't I? It's not working. Okay. So this is the Audubon guide. And it has all this handy stuff in it. And this is what we use in the labs. It's got star charts in the front. It has by season. And then it has by constellation. And they're alphabetical. And then it has pretty pictures of deep sky astronomical objects, which you will never see with your naked eye, but you could see with a camera if you had a CCD attached to it, and asteroids and things like that. And then it has lots of useful information on literally everything. And so this is a really great resource. It's also not the best resource for the Southern Hemisphere. It's got lots of information in it that you can use in the Southern Hemisphere, but for the Southern Hemisphere, you're going to want something more like this. This sucker is out of print. And I haven't really found a good substitute for it yet, so I'm interested in finding one. So this is the Australian sky. If you can get one of these things were beauties back in the day, and they're really great little guidebooks. And I'm still looking for an alternate now that these aren't in print anymore. And I think that's basically it.
All right, thank you, Jackie. We went a little bit over, but I think we're okay. So we're at 11:11 here, hour 11. So I think that'll wrap it up. So thank you, Brent. Thank you, Jackie. Thank you, Becky. And thank you, everyone out there who watched our first Google one. We'll do another one toward the end of the class where we'll shift it by 12 hours. So that way over the course we cover almost the entire globe. Okay, thank you. Bye-bye.
Thanks.